So here we shall uh, explain some theorems on composite functions and invertible functions with some examples. So the first theorem on the composite function is that if the function f maps from the set x to the set y, and g is a function which maps from y to z, so y and z are two sets, and h is another function which maps from z to the function s. So these are three functions. Then h of g of f, that is equal to h of g of f. So we can understand this theorem by one example. Example is that consider the function f which maps from the set n to n, where n is the set of all natural numbers, and g is the function which also maps from n to n, and h is also another function which maps from n to r, which is defined as the function f of x equals to 2x and g of y equal to 3y plus 4, and h of z, that is equal to sine z for all x, y, and z in the set n. Then show that h of g of f, that is equal to h of g of f. So now we have, so now therefore h of g of f, that is equal to h of g of f of x. So h of g of f of x, that is equal to this. So now that can be written as h of g of f of x. So that is equal to h of g of, now f of x is 2x. Now that is equal to h of g of y is 3y plus 4. So g of x is 3. So this will be 3 into 2x plus 4. So that will be h of 6x plus 4. So that is equal to, so h of z is sine z. So this will be sine of 6x plus 4 for all x belongs to n. And then this h of g of f of x, that is equal to h of g of f of x. So that will be h of g of 2x. So that will be h of g of 2x. It will be equal to h of g of 2x is 3 into 2x plus 4. So that will be also h of 6x plus 4, which is equal to sine of 6x plus 4 for all x belongs to n. So therefore we can see that these two are coming same, means h of g of f, that is equal to h of g of f. So hence proved. Hope you have understood this theorem on composite functions of composite of three functions h of g of f. And then the next theorem is that let f is a function which maps from the set x to y, and g is a function which also maps from y to z. So these are two invertible functions. So f and g be two invertible functions. Then g of f is also invertible. G of f is also invertible with g of f whole inverse, that is equal to f inverse of g inverse. So we can understand this by one suitable example. So it is asked to find that consider F maps from the set 1, 2, 3 to the set ABC, and G be the set G maps from the set ABC to the set apple, ball, and cat. Apple, ball, cat, which is defined as, so they are defined as f of 1 is equal to A, f of 2 is equal to B, and f of 3 equal to C, and g of A equal to apple, and g of B equal to ball, and g of C that is equal to cat. Then it is asked to show that the functions f, g, and g of f, and g of f are invertible. Then find out f inverse, g inverse, and g of f inverse, and show that g of f whole inverse that is equal to f inverse of g inverse. So now we can see that both the functions f and g are 1, 1 and onto. Both the functions f and g are 1, 1 and onto functions. It means they are bijective functions. So they are invertible also. So now therefore f inverse that will map from the set ABC to the set 1, 2, 3, and G inverse will also map from the set apple, ball, cat to the set ABC. So now therefore f inverse of A so now here it is told that f of 1 equal to A, so it means f inverse of A that should be equal to 1, and so f inverse f of 2 that is B, so f inverse of B that is equal to 2, and f inverse of C that is equal to 3, since f of 3 is C. And also G of A that is apple, so G inverse of apple that is A, G inverse of apple that is equal to A, and G inverse of ball that is equal to B, since G of B is written ball, and G of C that is cat, so G inverse of cat that is equal to C. So now therefore f of f inverse f of f inverse that is equal to identity of on the set ABC, Since why, if you do f of f inverse a, which will be f of 1, that is again a, and f inverse of f, that is also equal to, so suppose for example, if you do f inverse of f of 1, that is 1, so it will be identity on the set 1, 2, 3. And similarly, g inverse of g, that is equal to, so g inverse of, suppose g of a, that is again a, g inverse of g of a, okay, so it will be the identity on the set ABC, and g of g inverse, that will be again the identity on the set apple ball cat, or identity on the set D. You can say identity on the set D, where the set D is apple ball cat. So it means that f inverse exists and g inverse also exists. So now, therefore, g of f, that will map from the set g of f, g of f. So it will map from the set 1, 2, 3 to apple ball cat. It will use so the domain of g of f should be equal to the domain of f, which is 1, 2, 3. Domain of f, which is 1, 2, 3, and that will map to the range of g of f will be same as the range, or the codomain. The codomain of g of f will be same as the codomain of g, which is apple ball cat. So it will map from 1, 2, 3 to apple ball cat. So we know, so it will be like g of f of x, g of f of 1, suppose for example, which is g of f of 1. So that is g of f of 1, which is a. So it is g of a, that is apple. And similarly, g of f of 2, that is equal to g of f of 2, which is g of b, that is equal to ball. And similarly, g of f of 3, that is equal to g of f of 3, which is equal to g of c, that is cat. So now, therefore, we can also define g of f whole inverse. That will map from the set apple ball cat to 1, 2, 3. Apple ball cat to the set 1, 2, 3. So we can define g of f whole inverse as g of f inverse, g of f whole inverse of apple. So that is equal to cat. No, that is equal to 1. And then g of f whole inverse of ball, that is equal to 2. Since why, g of f of 2, that is ball, we have found it. And then g of f whole inverse of cat, that is equal to 3. So now we can also say, we can see that g of f whole inverse of g of f, that is equal to, so g of f whole inverse of g of f of, suppose 3, that is equal to 3. So that is the identity element on the set I 1, 2, 3. And g of f of g of f whole inverse, g of f whole inverse, that will be equal to the identity element on the, so if I do like g of f inverse of cat, so that would be g of f of 3, that is equal to cat. So this will be the identity element on the set D. So therefore we can say that all these functions f, g and g of f are invertible functions. Since why their inverse exists. So now f inverse of g inverse of apple, suppose. So that will be f inverse of g inverse of apple. So that will be, so g inverse of apple, that is a. So that will be f inverse of a. Now f inverse of a, that is 1. So now which is same as g of f inverse, which is same as g of f whole inverse of apple. And also similarly, you can see that f inverse of g inverse of ball, that will be equal to f inverse of g inverse of ball. So now here we have shown that g inverse of ball, that is b. So f inverse of b. So that f inverse of b, that is 2. So that is 2. And 2 is again same as g of f whole inverse of ball. G of f whole inverse of ball. And again similarly we can say that f inverse of g inverse of cat, that is equal to f inverse of g inverse of cat. So that will be f inverse of, so now g inverse of cat we have found, that is c. So that will be f inverse of c, that is 3. So that is 3. So 3 is again same as g of f whole inverse of cat. G of f whole inverse of cat. So hence we can see that these functions, their outputs are coming same when the input is the set n element from the set D. D is the set this which we have told. Okay, so therefore we can say that g of f whole inverse, therefore that is equal to f inverse of g inverse. So hence proved. So hope you have understood the two theorems on the invertible functions and on the composite function. Thank you.